Marco. I hope you can all hear me now.
Yes, we can hear them. We see what we are supposed to see.
Fantastic. So it's great to see everyone here, or for everyone to be here, and I'm very honoured to be invited to give a talk here. So thank you very much. And so I'm going to talk about a project that we did estimating expert review quality scores for journal articles with Bibliometrics and artificial intelligence. And this is a project with the other people on this slide. So it's a joint project from all of us. There is a copy of the slides on Figshare. I'm a little bit worried that you might not be able to see the detail of some of the graphs on the Zoom share. So, but if you can't see the details, you can maybe have a look at the copy of the slides on Figshare. Okay, so I'll give a little bit of background and then go through the study and then some follow-up studies that we did with this project. So a little bit of context first about the UK Research Excellence Framework, or REF 2021. I'll just explain what it is for those of you who aren't in the UK, and therefore this doesn't dominate your life, your working life. So REF 2021 used expert review to score 185,594 research outputs. And these are mainly journal articles from 76,132 staff in 157 UK higher educational institutions, mainly universities. So this is at least one output from every active researcher in the entire UK was assessed by expert review and given a score. And REF also covered the impact of research, the societal impact of research, which counted for 25%, and the environment, the research environment of the universities, which counted for 15%. But the majority of the overall scores came from the journal articles and the other outputs. And I'm just going to focus on the journal articles in this talk. And everything was given a 4-point scale score. So 4-star was the top, meaning world-leading research, 3-star internationally excellent, 2-star recognized internationally, and 1-star recognized nationally. And there were about 4 pages of descriptions about all these categories, and the descriptions varied between 4 different fields, broad field groupings. So the assessors were told roughly what all these terms mean, but I'll just use the 1-star, 2-star, 3-star, and 4-star. And the experts were 1,120, mainly senior professors, and they were organized into 34 field-based units of assessment in the UK jargon to assess the work. So essentially broad fields or groups of related fields. And this is this was done by 2 experts per output. So there were 2 primary assessors for each of the 185,000 outputs. And there was norm referencing within the units of assessment and overall across the whole of the REF. So this was a very serious attempt to get fair scores for research outputs, for a very large number of research outputs from the UK, representing outputs that were produced between 2014 and 2020. So the overall admin cost was estimated to be more than 240 million, so a big exercise. But the results were used to direct 14 billion in block grants until the next exercise. So it's really enormously financially important exercise, which is why they took it very seriously. All the stages seem to be taken very seriously and run very carefully. So just some examples of the units of assessment. Unit of assessment 9 is physics, and that would include some scientometric applications. 11 is computer science and informatics. Again, a little bit of scientometrics. 17, business and management studies, and that would include some research policy and scientometrics. And 34, communication, cultural and media studies, library and information management. So I would say that's more or less the home of scientometrics, the core place for scientometrics, although there wasn't much scientometrics in the UK published. So this is just to give you a flavour of what the different units of assessment were. Okay, so what did we do with this project? So our specific goal with the project, so this was a UK government-funded project to assess whether artificial intelligence could inform or replace expert review for the journal articles in future refs. So I've already mentioned that 1,100 experts assessed these articles. So it probably took them about up to half a year each to do this job. They all had over 100 outputs to score. So this means we take a substantial minority of the UK's research experts and say, for half a year, you're not going to do research. You're just going to score research. So this is obviously not a good thing. It's very expensive and it's widely complained about. So it's logical to assess, okay, could we replace the human experts with a computer that will do the job much more cheaply, maybe quicker, and save the time of these experts and let them do research instead? So we were given the provisional ref scores, and we were allowed to analyse them for 2 months between March and May 2022. So they've been destroyed now. So it's UK government policy to destroy these scores for individual articles before anyone's told the results. And the institutions are not told the scores for individual articles, but they're only told the aggregate scores. So they'll know, for example, if a department submitted 50 outputs, they would know that 20 of them got a 4-star, 10 got a 3-star, etc. But they wouldn't know which ones got which grade. So they deliberately are not told that information. So we were told that information, and we were allowed to hold on to that information for 2 months. And at the end of the 2 months, all the data had to be destroyed. So we needed the individual scores so that we could assess whether the machine learning methods, the artificial intelligence that we'd used, were accurate or not. So the methods we used, well, we tested thousands of combinations of different machine learning algorithms, inputs, and broad strategies to see which worked best. And we tried to do it in a way that isn't cheating or leading to overfitting. So I won't go into details, but I'm happy to answer questions about that. So that was quite tricky. And then after we'd got the results, we discussed the results with a series of focus groups of assessors from Ref 2021. So the experts that had done the assessment in the first place, we asked, are our suggestions or are these results reasonable for use in the future Ref? Okay, so part one, the project methods and results. And then in part two, I'll go through some additional findings we got. Since we had the data, we did some extra studies with the data. So the project methods and results. So what do we use as the inputs for the machine learning? So we used a standard machine learning strategy, and we fed the machine with information about the journal articles, and then we asked the machine to predict whether each article was 1-star, 2-star, 3-star, or 4-star. So the inputs we gave were citations, obviously. So we told the machine how many citations each article had, and we field and year normalized this because the units of assessment are, some of them are quite cross-disciplinary. A research team size, so the number of authors, institutions, and countries contributing to the paper, because this is known to associate with citation counts. So it might also associate with research quality. And we also added some data on the track record of the research team. So how many articles the first author had written during the ref period, and the average citation rate of the Scopus Index journal articles written by either the first author or any author during the ref period. So both of these things were trying to measure or trying to get an indicator of how successful the research team were that produced the individual submission. And then for document properties, we looked at the readability of the abstract, which is sometimes shown to associate with the quality, the citation impact of an article, and also the length of the document. And we also included a measure of the citation rate of the journal, not the journal impact factor, but something similar with a similar philosophy to the journal impact factor. So what we think is a statistically better version of the journal impact factor, And this was included as a measure of the prestige of the journal in which it was, in which the article was published. And we also included some text from the title and the abstract, so words and short phrases, up to 3-word phrases from the title and abstract. So this is the only thing that's really about information about what the article is about. And we also included the names of the journals. So the 2 red things are the things that we added after our preliminary tests, and everything not in red were inputs that we'd already decided on before we had the data. So we tried to not change the predefined inputs to reduce the chance of the cheating, overfitting in the machine learning. So we added the journal names because there's some good journals are not very highly cited, and some highly cited journals are not very good, probably. So we added the journal names as a way to kind of bypass the journal impact factor type input that we had when it was necessary. Okay, so first screen, I hope you can see the tiny little writing on this. If not, please have a look at the copy in the Figshare. So these are the overall results. And this graph shows for all of the 34 units of assessment, and then the 4 broad groups at the top. So the ones at the top are the broad groups. So A is health sciences, B is physical sciences, C is social sciences, and D is arts and humanities. So on this graph, it shows the baseline accuracy, so without machine learning, and then the accuracy that we achieved with machine learning. So where the blue bar is much bigger than the orange bar, then the machine learning is essentially working to some extent. And this comes from showing the machine half of the articles and then asking it to predict the other half. And then we measure the accuracy on the other half. So the bad news for us was that the accuracy was always below 75%. I think 74% was the highest we got for any field. And in many fields, accuracy wasn't much better than the baseline. So what's the baseline here? The baseline is predicting that every article gets the majority class. So either every article is 3-star or every article is 4-star, depending on the unit of assessment. So in some fields, we couldn't get an accuracy from the AI that was higher than just the stupid, simple method of classing them all as 3-star or 4-star. So, for example, on unit of assessment 34, using AI was slightly less accurate than giving every article 3-star. So the AI just didn't work at all on 34, on unit of assessment 34. So if we zoom in from the previous slide on the units of assessment where it did work a bit better, so these were the health sciences at the bottom and the physical sciences and economics, and to some extent business. So here the AI could go substantially beyond the baseline of giving them all 3-star or 4-star, and this was primarily because of the citation information and the journal impact information. This was the most powerful input to the machine learning. So we could predict with much better than a baseline accuracy, but still the accuracy isn't high. So it's still not we've still not got a machine that can replicate the human. So overall, how accurate are the predictions? So for the top 8 units of assessment, the 8 units of assessment where they're most accurate, the accuracy was 65% to 74%. So moderately high, but certainly nowhere near. So not in the 90s, for example. So not essentially the same as the humans. So health sciences, physical sciences, and economics. So looked at from a different perspective, if we average the results across the departments, which is where it's actually important, we don't really care about the individual scores. What we really care about is whether the average for the department changes, because that's all the departments see. The departments don't see the individual scores, they just see the average. So the correlations actually were very high, depending on how you actually count them and in which unit of assessment. So the highest correlation between the AI predictions totaled and the human scores total was 0.998. So virtually one Pearson correlation. I think that was unit of assessment 1, but that's for the total of all the scores. So adding all the scores up rather than averaging them. So if you average them instead, then the highest correlation is 0.906. So still a high correlation. So it would be plausible to argue that, okay, the individual results aren't that good, but once you average them, which is the important thing, then the correlations are very high, maybe high enough to say that it's worth saving the human time and using the AI. But we showed the results to the URA assessors in our focus groups, and virtually all of them were unhappy with the score shifts. Even with a Pearson correlation of 0.998, they were still almost all unhappy with the score shift. So I think there were 3 out of about 25 that expressed a willingness to go with the AI and accept the score shifts that we get. So why were they unhappy with a very, very high correlation for the total score? And because it's the total score that affects how much money they get. So if the total score doesn't change very much at all, then the amount of money out of the 16 billion, was it, that the university gets won't change much at all. So that was what I was personally most interested in. But most of the assessors were more interested in the rankings between universities. And the rankings between universities do change, even for small changes from the human to the AI rank. So this is a bit of a strange graph. So this shows the ranking changes from the AI. So we ran the AI 10 times and we looked to see the average ranking change for an institution and the minimum and a maximum. So the blue line here, this is the average ranking change. Each dot represents a university. And in this example, this was clinical medicine, unit of assessment 1. There was only one university that in all 10 tests didn't change its rank. It had the same rank all the time. But every other university had a rank change. So this was one of the most accurate prediction units of assessment. But even with this one, there was one institution that might have lost 7 places in the ranking table. So it might have gone from, I don't know, 25th to 31st in the ranking because of the AI replacing the human. So the assessors saw this and said, okay, we don't want that. So some universities like this one would almost certainly lose out from the AI. Some would almost certainly gain from the AI. But for most of them, it was a little bit random. They might gain or lose 1 or 2 places from the AI. So this uncertainty and random unfairness, or potential for random unfairness in the system, was something that the assessors were not prepared to put up with. So essentially the problem was we could get at the department level very accurate predictions, but we couldn't get at the ranking level very accurate ranks for departments, and therefore the assessors didn't want it. So a few follow-up questions. Could we have produced a more accurate system? So we only achieved 74% accuracy at the individual article level. Could we have been more accurate? And the answer is, with machine learning, is yes, you can always do better. But we did try all the methods suggested by the literature review. And we have produced by far the highest recorded accuracy for any ref-like prediction task. So no one's got anywhere near 0.996 before. I think the highest previous was 0.946 for a correlation. And we think that very high accuracy is a logical impossibility because it's difficult to replicate the expertise of reviewers, and really it's probably impossible to replicate their expertise with AI. So if you think about the expertise of a reviewer, so a ref reviewer here, they will have a lifetime of research experience inside their head, a lifetime of knowledge from reading books and journal articles, a lifetime of discussing with the community, other researchers, what is quality, what's good research, what's bad research. And then they will read the ref papers and the scores. They'll read the full text of the papers and the scores. And based on that, and reading the full text of a ref article, they'll make their judgment. But the computer program, the AI system, it doesn't have the research experience, knowledge, community discussion, or full text of ref articles. All it has really is a big bibliometric database. So its big advantage is a massive bibliometric database. And it'll have metadata of ref papers like the article and the title, the title and the abstract of an article. And then it will have to make a judgment on the basis of a ref article and its metadata. So it has much thinner information. So it's not really surprising that it can't do what an expert can do based on a much simpler brain, a much simpler brain, and much less information. So that's my argument anyway. So coming back to the reason why the assessors were not happy with the results, one problem that we had essentially was the human factors are undermining the credibility of the AI. So as I mentioned, it's the use of the league tables and the grade point averages. This was a human factor that meant that although a technically good solution was produced for some units of assessment, it was the rankings, the human value given to the rankings that was killed it off. And this is despite the fact that universities are told do not produce rankings with this data. So they're told very clearly, repeatedly, but they all immediately do. And a second limitation was the need to treat submissions the same irrespective of size. So treating every institution the same is kind of a mantra in the ref. And we could have produced slightly more accurate overall results if we used different strategies. So we had to use less AI on the smaller submissions. We could have had a more accurate overall result with smaller ranking changes. But we asked the ref assessors and they all said, every single one of them said, no, you can't do that. We wouldn't accept that. So one of the technical partial solutions was ruled out. And really the big thing at the end was we didn't know how accurate the humans were. So if we'd have known that the human assessors were, say, 85% accurate or 90% accurate, we could have reported, okay, we've achieved human level accuracy on this data. So at the moment, the kind of implicit assumption is that the humans are correct and the AI makes mistakes. But in reality, the humans make mistakes, the AI makes mistakes, and we don't know which one makes the most mistakes. So that's a big limitation. So we're asking the ref next time to allow us or someone else to assess the accuracy of the ref assessors in some way. So at the same time, we also looked for bias in the AI system. So we were asked to check for bias in the AI. And we found that the AI predictions were not systematically biased by first author gender, male or female, didn't make any difference to the AI predictions. Whether the submitting author was an early career researcher or not, didn't make any difference to the AI. And whether the article was interdisciplinary or not, didn't make any difference to the AI. So it didn't introduce any of these three types of bias that we were able to test for. But there were biases in the predictions that we did find, although ones that we could compensate for with technical solutions. So there was a small bias against larger institutions, against larger submissions to a unit of assessment, and a moderate bias against the higher scoring submissions. So this was the most worrying of all the biases, really. So a university that got a very high score, if you replace the human assessors with AI, at least partially, then their score would decrease a little bit on average. Or a low-scoring unit of assessment, low-scoring institution, its score would increase a little bit. And that was probably a regression to the mean effect. If the AI makes a mistake, it's more likely to make a mistake downwards for a higher scoring institution, for example. And again, the biggest error in terms of the averages, were for smaller submissions. So we could eliminate this, but the assessors wouldn't let us. So we talked about different strategies for using the AI in assessments, making recommendations to the UK sector. So I'll just briefly go through the ones that we discussed at the end. So we were asked to test for the classical machine learning strategy strategy, which is to get the AI to predict half of the articles and the humans to predict the rest. And we thought that this could be done for nearly 13,000 of the articles from 5 of the units of assessment where there was a high accuracy, and it would give a labor saving time. So it would allow 90 of the assessors not to do any assessment. But this wasn't recommended because in our focus groups, the score shifts were thought to be too large. And we tried a different strategy, which I haven't shown results for, which is only to allow predictions when the AI was at least 95% confident that it had the correct answer. So this will give a smaller labor saving, just under 3,000 articles. But again, the score shifts were still too large for our focus group. So that's not recommended either. Third strategy, inform but not replace. So the classical bibliometric strategy. So for this strategy, we would supply the predictions and the probabilities that the predictions were correct to the UI experts and allow them to use those predictions to help them make their decisions if they wanted to. So they might use them as tiebreakers when the 2 experts disagreed, or they might just accept the very high probability predictions without reading the articles, or with only 1 instead of 2 assessors reading the articles. And we nearly recommended this, although it wouldn't save any labor, but it would improve score accuracy, we think. Well, we didn't recommend it because essentially its value was small, and it has a perverse incentive in the UK context to publish in high impact journals because we included journal citation impact as one of the inputs. So it would have a small advantage, but run against the responsible research initiatives in the UK at the moment. So that was the reason that we didn't recommend it. So we think it's a technically good solution, but ethically isn't a good solution in the UK at the moment, although it might be a reasonable solution for other countries if they don't have the same focus on journal impact. And so what we did recommend in the end was to pilot test for the next ref and then try to assess again whether it will work for 2034. And we've made specific recommendations for the pilot testing, such as assessing human error and encouraging research into extended predictions for ref-like data, and encouraging institutions to make the full text of the articles available in machine-readable form, which we didn't have for our data set. So only about a third of the articles could be found online in machine-readable form. Okay, so that was the end of our recommendations for the project to investigate whether AI predictions could inform or replace, or partially replace, the human scorers for the UK Ref 2021. Okay, so the second part, so I'd like to talk for the last quarter of an hour about 7 additional bibliometric findings that we got from the data that they shared with us. So because they'd given us over 100,000 expert quality scores for journal articles, we ran a series of tests to see whether that would help us give insights into the value of citation type data in research assessment. So I'll run through these fairly quickly. Each one is a journal article, but I'll just give you a summary of the results. So first of all, we tested, is citation impact a good quality indicator? So are articles more highly cited? Are articles that are more highly cited more likely to be high quality? So we calculated a Spearman correlation between the quality score of an article and the citation impact of the article, field in year normalized citation impact of the article. And this graph shows that yes, for every field, every single field, but it varies greatly. So chemistry at the bottom is the field in which citations are the most powerful indicator of research quality. And at the bottom is classics, where they possibly no association at all. So yeah, varies greatly between scores. So the bars show 95% confidence intervals. So unit of assessment 34 here. So there, this is definitely true that more cited articles are more likely to be higher quality in unit of assessment 34. So we have a definitive answer for across the full range of disciplines for journal articles, that there's no field in which there's clearly a negative association, and in almost all fields there's a statistically significant positive association between citation rate and research quality, but it's never a perfect. So even there's slight relationship in the arts and humanities, but still positive. But again, citation impact is never a quality measure because the association is never very high. It's only up to moderate to strong in chemistry. Okay, so the second study we did, the second question we asked was, if you've got a very highly cited article, is it definitely world-class 4-star quality? And we asked this question because a senior person in the UK told us essentially as a fact, this is true. All the highly cited articles will be 4-star. So we checked that and it wasn't true. So it was nearly true in chemistry at the bottom here. So in this graph, we're showing the proportion of the 25 most cited articles in each unit of assessment, what proportion, so the average score of them. So if all the top 25 articles got 4-star, then these bars would go up to 4 here. So in every field, at least, in every unit of assessment, at least one of the top 25 most cited articles was not allocated a 4-star. But in the fields where citations are a good indicator of research quality, then most of them were 4-star. But in other fields, there could be, most of them could have been much lower, 3-star. So in 34, so 3. So the 25 most cited articles in unit of assessment 34 varied between 3-star and 4-star, and more of them would have been 3-star. So the answer is definitely no. Being highly cited is not a guarantee of being high quality. So if you look at a list of the top cited articles in any field, they will not all be world-class quality. That's what this says. On the other hand, it could be due to scoring errors. And so we can't rule out human error as a possible reason. So we can't be too definitive in the conclusions. But I think it's more likely that we have some highly cited routine contributions creeping in the top lists. Okay, the next thing we looked at is journal citation impact a good indicator of quality? So if you have a journal with a higher journal impact factor or more highly cited articles, does it also tend to publish more high quality articles? So are things like the journal impact factor a good indicator of research quality? And so we use the same strategy, correlate the average journal impact, not the journal impact factor, but our own version. Does that correlate with the quality of the journal articles published in the journal? And it varies between the units of assessment, but in general, yes, it does. So the associations tend to be a bit weaker depending on the field, stronger in some fields than the citation rate of the individual article, but the correlations tend to be weak to moderate between the journal citation rate and the article quality score. So in all units of assessment, journals with a higher citation impact did tend to publish higher quality articles. So the journal impact factor is not completely irrelevant, which I think we know anyway. But we also checked whether there was any journal that always published 4-star articles. So before this, I would have guessed that journals like Science, Nature, British Medical Journal, and New England Journal of Medicine, and Cell, all their articles would be 4-star. So we checked to see if there were any journals which all their articles were 4-star, and the answer was essentially no. So we checked every large journal, every journal with more than 50 ref articles, and none of them always published had all their articles given the same score. So no journal with more than 50 articles in the ref always gave a 4-star. So there was some Science, Nature, British Medical Journal, New England Journal of Medicine articles that were not given a 4-star, which astonishes me, because I would give my right arm, as the saying goes, to have a publication in any of those. But it could be due to the submission of small contributions to top journals. Yeah, so again, there's no shortcut to knowing that an article is high quality. So what does a weak correlation mean for these journals? So I've got some extra graphs on journals. So for all of the Scopus categories, so these graphs are for Scopus categories, not the units, UK units of assessment now for technical reasons. So we've got a graphs illustrating the correlation for all of the almost all the Scopus categories. And for the social sciences Scopus category, this is illustrating a correlation of 0.22. And we can see that if you've got a 1-star article, then the journal citation impact, like the journal impact factor, could be very low, could be moderately high, probably is reasonably low. Whereas if you've got a 4-star article, again, it could be in a very low journal impact factor article, could be in a very, very high journal impact factor article, but it's more likely to be in a moderately high journal impact factor article. So you get a spread in the journal impact between the different 4 categories. That's the point of this violin plot. So if anyone tells you, well, this article is in a very high impact factor journal, therefore it's brilliant, you can show them this graph and say, well, not really. There's a different possible quality levels it could be in, even though it's in a very high journal impact factor article journal. So if, for example, your very high impact journal could still be a 3-star, could still be a 2-star, but couldn't be a 1-star. Okay, next one. Why are co-authored academic articles more cited, higher quality or larger audience? So if you're interested in why articles with more authors get more cited, you might think that they're more cited because they're higher quality, or you might think they're more cited because there are more authors and therefore they get a larger audience from friends of the authors, or people that know the authors, or people from the same country as the authors. So we tried to test with this with our data. So we correlated the Rev quality scores against the number of authors by unit of assessment, and we found that articles with more co-authors are usually higher quality. So there are moderately strong correlations in the health, life, and physical sciences between the number of authors and the quality of an article, the Ref quality of an article, but weak or no positive associations in engineering and social sciences. So author numbers not so important in engineering and social sciences, and then could even be negative in the various arts and humanities. And possibly negative association in the decision sciences. So if you're a statistician, it might be better to write on your own than with colleagues. But outside the decision sciences, it either makes no difference or it's a help, depending on your field. No cause and effect claimed, however. And we also tried to check if there was kind of a residual audience effect despite the obvious quality effect, and we found that there was. So there is an audience factor in some fields, not necessarily all, but in some fields, co-authors do attract citations. So articles are more cited, but they're not higher quality in some fields. So here's the graph for correlations between the number of co-authors and the quality of an article. And you can see in, for example, public health, the bigger teams give you better research. But in philosophy, probably doesn't, the team size probably doesn't matter. And for this is the correlation between the same correlation, but for Scopus categories, not unit of assessment. So it's the same graph as before, just different categories. And you can see here the decision sciences, that's got a negative correlation. Small teams are better in the decision sciences. It doesn't make much difference, though. And then these are Spearman correlations between field normalized citation counts and number of authors, and not the quality score. This is the citations and the number of authors. As you can see that in every field, having more authors gets you more citations. So logically, this means that in some fields, having some more authors doesn't get you more, it doesn't get you higher quality, but it does get you more citations. So therefore, there is an audience effect in some fields. Okay. So on to the next one, nearly the last one. So we also looked to see if research with funding tended to be higher quality in all fields. So we used regression for this one because we wanted to factor out the number of authors, because funded research tends to have more authors. And we found that funded articles tended to have higher ref scores in all units of assessment, even after factoring out collaboration. And again, we can't claim cause and effect, but funded research does tend to get a higher quality score. And sixth, we looked for bibliometric biases for gender, institution, and interdisciplinarity. So, and again, we compared the ref scores to the citations by gender and institution and interdisciplinarity, and we did it separately for citation rates and journal citation rates, article citation rates and journal citation rates. And we found that bibliometric scoring slightly advantages women compared to men, especially in the physical sciences, engineering, and social sciences. So bibliometrics doesn't disadvantage women if it's introduced into research assessment. So this is a little bit of a surprise, given that bibliometric-based rankings tend to favor men, but they don't in this context. And we found that bibliometrics or journal impact scoring disadvantages departments publishing high-quality research. So even though they'll tend to publish highly cited articles in high-impact journals, it still disadvantages them if you introduce bibliometrics into a research assessment. And interdisciplinary research, it kind of varies between units of assessment, whether it gains or loses from the introduction of bibliometrics. So that's a more difficult case. So this graph shows the gains or losses for women compared to men from citation rates, the blue bar, or journal impact, the orange bar, and the confidence intervals almost all contain 0, but they're mostly above 0, suggesting that overall the trend is for women to slightly gain from citation-based data in a peer review exercise. And finally, do altmetric scores reflect article quality? So altmetrics were designed to reflect aspects of quality not reflected by citations. So we tried to check if that was true for the ref quality scores, and we used data from altmetric.com and Mendeley, correlating them with the peer review scores from Ref 2021. And Mendeley reader counts worked best. So 3 of them correlated in 3 fields. The Spearman correlations were 0.05. So they work similarly to citation counts, Mendeley reader counts, unsurprisingly. And we found that tweet counts are a moderate strength indicator of research quality in 8 units of assessment, and they're ahead of news, blogs, and Facebook. And they were strongest in the physical sciences and health, and they were weakest in the arts and humanities. So this was disappointing. We were hopeful that tweets would be a useful indicator in the arts and humanities where citations aren't useful, but it's the other way around. So that's a disappointment, because we still have nothing really good in terms of quantitative indicators for the arts and humanities. So this is the graph of the correlation for some of the altmetrics and research quality, and just zooming that in a bit to the lower ones. So for example, for clinical medicine, tweets, the number of tweets in an article is actually a moderately powerful indicator of the quality of the article in clinical medicine, a bit better than news, blogs, and Facebook. Okay, so finishing off, so we've seen in this talk, so I've tried to argue in this talk that machine learning can play a minor role in supporting but not replacing expert research quality judgments, even though we didn't recommend it for the UK. We do need more research into the accuracy and particularly agreement level of expert reviewers in ref-like exercises if AI is going to be taken up. And we saw in part 2 evidence of field differences in the value of citation-based indicators and the role of funding and collaboration. So thank you very much for listening, if you have, and happy to take any questions. And if you're interested in more information, all the publications mentioned here can be found from the URL at the bottom.
Thank you so much. And we have time for questions, and I'll try, yes, to convey in case you don't really hear the questions. And I have one question from Vincent Trug. Let's hope that you can hear Vincent.
Hi, not sure if you can hear me directly.
Yeah, I can hear.
Okay. Yeah.
Nice.
Hi, thanks for the talk. Wonderful array of different types of results that you have. So there's 2 elements that I want to touch upon. So I think it's great that you're recommending, let's say, looking into the human error part, because I think many of the results of the correlations are difficult to interpret by yourself, and what is a high correlation if you're not sure what the error might be in the human part. The other thing is the role of institutions themselves. And so in the slide where you showed nicely the human brain versus the machine brain, so to speak, the human brain had a lot of different types of knowledge behind it, all types of things that it could take into account. But one very particular aspect is, of course, the institution itself. So later you mentioned that there is a bias against high-scoring institutions by AI. You could also turn it around, I think. And arguably, it could be a human bias in favor of, well, high-performing institutions. And so you might expect that institutions that are well-known and reputable, Oxford, Cambridge, and whatever, they will score highly on a particular publication, not because the publication is so great, but hey, it's Oxford, it's Cambridge. And so humans take it into account. AI does not. And so I was wondering whether you have taken into account at one point, or at least trying to see if we take institutions into account in AI, what would the results actually be? And would they agree with, would assessors essentially agree with the type of ranking that would result from that type of prediction? I'm not saying that that type of prediction would be good, because it would give a sort of a perpetual type of favoritism for particular institutions, but it might indicate that it's actually perhaps human bias that creeps in there, disadvantaging certain institutions that should have actually had a higher score. Thanks.
Yeah, thank you very much for that question. So yeah, that was an interesting question. So we did think about this during the project, and there was an accidental feature of the data, which was that some of the articles, so you could have an article submitted to the ref by different institutions. So some articles were scored more than once because they've been submitted by different institutions, and they'd either been submitted to different units of assessment because they were interdisciplinary, or they'd have been submitted twice to the same unit of assessment. So there were a number of articles that had been scored more than once, but submitted by different institutions. So you could have an article submitted by, say, Cambridge University, co-authored with another UK university, say Luton University, and it got 2 scores, one as a Cambridge University article and one as a Luton University article. And we looked at all of these articles which had been scored twice for 2 different institutions, and we found that there wasn't a systematic bias. So we expected to see that the Cambridge one would get the higher score systematically than the Luton one, but it wasn't the case. So occasionally the Cambridge one would get the highest score, occasionally the Luton one would get the highest score, but on average, the difference was, I forget the exact difference, but overall the difference was very close to zero. So we did expect to see institutional bias. So I personally expected to see a strong institutional bias, but in the data that we saw, obviously this was only for a small fraction of the submissions, we couldn't find evidence of a bias. So it could be that there are different types of bias in different types of units of assessment, institutional bias, but it's quite possible that there isn't really an institutional bias in the ref. So if there is, it's not a strong institutional bias, not strong enough to appear in the data that we had. Yeah. So we could, it would be interesting to test that further though, in the next ref exercise. Thank you.
We have another question.
Yes, my name is Michael from the IT University in Copenhagen, Denmark. Thank you for the presentation. It was super interesting, especially the last part of all the correlations. But I have a question for the first part where you create the model, and you mentioned that you used journal names. Could you say a bit more about how you use the journal names in the model?
Okay, thank you very much. Yes, so with the journal names, the reason why we introduced them was because we saw that there were some big high impact factor journals that we didn't think were high quality, essentially. So we thought the model was being, the power of the journal impact was being broken by these big journals. So we introduced the names of the journals as a way of allowing a journal to be taken out, essentially, by the machine learning method from the journal impact factor type data, so effectively. So what we did was we had a set of 11 standard bibliometric inputs that every machine learning method got, and then we produced a set of over 100,000 extra inputs, which were all the words and all the 2 or 3 word phrases in all the titles and abstracts for the unit of assessment. And then we added to that the full name of every journal that was published in. So that this ended up with over 100,000 different inputs. And then as part of the machine learning phase, after the split between the testing and evaluation set, we used a feature selection to pick the 1,000 most powerful features, but we insisted that the first 11 were always kept. So this would have meant that essentially the end result of this would mean that any big journal name which was powerful at discriminating between different article quality scores would be kept in the data, and small journals would be thrown out, and journals that were not powerful indicators of the quality of an article, their names would also be thrown out. So I didn't check, but we probably had about 300 journal names maximum, maybe less than that, kept into the final data set. So the most useful, essentially, journal names would have been kept into the final data set for each run of the machine learning. There's a little bit of a roundabout way.
Yes,
so
I
it's
think
a tech.
Yes. Thanks for the answer. We have time for one more question, the last one. Yes, yeah.
Hello, my name is Jan Belleman from the Federation of Finnish Learned Societies. Thank you very much for a very, very interesting presentation. I have one question. Now you focus on 150,000 journal articles submitted to REF, but the entire journal article output from UK higher education institutions is broader, maybe somewhere around 250,000. Did you consider or think of applying the algorithm to that part of the UK output that is not submitted to REF and see how that part of the output is scored to the REF levels?
Okay, thank you. Yeah, that's interesting question. So the short answer is no, we didn't think of doing that. But that would have been interesting because one of the questions that the UK one of the issues around the ref is that we don't assess every article produced by UK researchers, as you've mentioned, but it would be possible to assess all the articles. So the question would be, would it make any difference? So if we'd have done exactly what you suggested, then we could have told the UK government, yes, it does make a difference, or no, it doesn't make a difference, or this is the type of difference that it does make. So yeah, so we've missed a trick there. Thank you. Yeah, we've missed a trick. We should really have done that, and then that would have got some. So next time, maybe.
Okay, thank you so much once again, Mike. And I'm sure everyone will go directly and read the papers, the GT's papers, the one you mentioned, to know more about the details of this important study. But once again, unfortunately, we couldn't give you in real life the book about Gothenburg, but you get to learn, yes, a little bit more about Gothenburg, the 400 years of this city. So thank you.
Yeah, thank you very much. It's a lovely book. I'm really pleased with that. Thank you very much.